Dongfeng, are you ready?
Yes, yeah.
Okay, good morning, good afternoon, and good evening. Welcome to the World River and Delta System Source to Think webinar series. And today we are great honor get Dr. Dongfeng Li from National University of Singapore come here talk about the impact of modern climate change on fluvial sediment delivery in high mountain Asia. So this webinar series is co-sponsored by NSF, NC State, Louisiana State University, State Key Lab, Estuary and Coastal Research in Shanghai, and Utrecht in Netherlands. So before I introduce Dongfeng, as always, I will say since August 2020, 2 years ago, we started this webinar series. So far, we have already hosted 130 talks. All those talks are already archived on our YouTube channel. So as you can see, simply you can see tinyurl.com/S2S talks. You can directly access all previous recorded talk. And at the same time, we also have a Twitter account, Source to Think, and all the upcoming talks and publication or related conference information we're posted over there. So as I mentioned, Dongfeng is a research fellow, like postdoc at National University of Singapore, and he got his PhD last year in the Department of Geography. His research mainly focused on climate change, glaciers, permafrost, river process, hydropower exploitation, and focused on particularly in Asia high mountain area. During his PhD, he assessed the impact of the modern climate change on landscape instability and the fluvial sediment fluxes and their implication for hydropower system in high mountain Asia. And he was awarded the IPCC Scholarship Award for Earlier Career Scientist and the best PhD thesis in the natural sciences in National Singapore University of Singapore. He also published a leading author article in Science, Natural Geoscience, Nature Geoscience, Geophysical Research Letter. Very impressive. His research has been widely featured by international media, including Scientific American and the Straits Times. So now he also self-associated of GIGR, Earth Surface, and a core member of the working Daniel Change Working Group and the International Associated Geomorphologist. So I think Dongfeng, now you can share your screen, and we're looking forward to your talk.
Thank you. Can you see my screen now?
Yes.
Okay, let me adjust the chat box and also here. Okay, the pointer. Oh, sorry. Is a point. Okay, yeah. Okay, thank you, powerful introduction. And hello, everyone. My name is Dongfeng Li, and I'm a research fellow in National University of Singapore. And today I'm very glad to have this opportunity to share some of my recent research progress with our Source to Think community. And today the title of my talk is about impacts of modern climate change on fluvial sediment delivery in high mountain Asia. So we are talking about the modern climate change, and the left figure is from the latest IPCC report. It shows the change trends of the global surface temperature of the past 2,000 years. So basically from this figure, we can see the global surface temperature since the 1950, 1960 has dramatically increased. And this is largely driven by the anthropogenic greenhouse gas emission. So when we are talking about the modern climate change, basically the time scale means the starts from the 1950. And climate change, modern climate change has huge impacts on many sectors for flooding, droughts, wildfires, and sea level rise. But for our geomorphologists or our source to sink community, we think we're really curious about the geomorphic and sedimentary effects of modern climate change. And talking this, I would like to recommend two papers led by Anne East. She did two very nice papers to get us to think about this big question broadly, not only focus on one aspect, but broadly to think about how the modern climate change can affect our geomorphic systems, including the slope stability, the watershed sediment use, and also fluvial morphology and the aeolian processes. When we are trying to summarize this commentary paper for us future, we am one of the co-authors here. We summarize the challenge and also the opportunity to measure and attribute the sedimentary and geomorphic response to modern climate change. There are many challenges due to the, for example, due to the data limitation, and also geomorphic systems are pretty complex systems, and sometimes it's not easy to see the climate change signal very easily. But there are also many opportunities. For example, we can focus on the study area in the cold environments where the signal to noise ratio is high. So for example, Kim Bilic is the chief editor of geomorphology. He's also leading the Daniel Change Working Group in under the IAG. So we can see in this book, source to sink fluxes in undisturbed cold environments, they really summarized from a global perspective on the sediment and also solute dynamics in the world's cold regions, including the Greenland and also the Western US and the European. A lot of studies in the European Alps and in Patagonia and Antarctica, and also in the New Zealand. So surrounding this big this area, the big question that we hope to address is how does the modern climate change can affect the fluvial sediment flux in cold environments? So this is the fundamental question that we hope to ask. And my study area focus on high mountain Asia, and in this talk I hope to cover three topics. First, I will introduce the climate change and cryosphere degradation context in high mountain Asia, and also secondly, I will focus on how this modern climate change can drive the increase of sediment supply and the sediment flux. And lastly, I hope to discuss the impacts of the changing sediment flux on the hydropower systems, water quality, carbon cycle, and flux. So high mountain Asia has many names, and it is very, for our earth scientists, I think it is a fascinating place to study, and a lot of researchers from worldwide to come here to study the climate, geology, glaciers, permafrost, river systems. And it is suitable for having this massive glaciers you can see from this blue shaded area, and also 40–50% of the landscapes in the high mountain Asia are underlain by continuous permafrost. So it is also the Asian water tower. All these large Asian rivers, including the Indus, Ganges River, Brahmaputra, Salween, Yangtze, Yellow Mekong, they originate from the high mountain Asia. And these large Asian rivers, they are not only contributing water resources for billions of people, but also they are important sediment sources for the global land ocean sediment budget. And climate change here is very fast. Some of you may have heard the amplified Arctic warming. Basically, it means that the Arctic is warming much faster than the global average. Actually, the climate change story in the South Pole is quite similar to the Arctic. So we can see the red line here is the Arctic, and the blue is the temperature change trends of the South Pole. So we can see they are very close over the past decades. And here we collect data from the temperature and also precipitation data from over 100 climate stations in the region. And we found that the temperature increased at a rate of 0.32 degree per decade since 1960. This is twice the global average, and precipitation also overall increased. So basically, we can say the climate in the high mountain Asia has become warmer and wetter in recent decades, especially since the middle 1990s. And in response to such amplified climate change, as I said earlier, there are massive glaciers here. They are experiencing a substantial glacier mass loss. So for example, in this map, the red dots means the negative glacier mass balance. And especially in the Himalaya and also in the southeastern part of the Tibetan Plateau, we can see the very negative glacier loss rate. And from this photos that very nicely recorded the thinning and retreating of the glaciers here in the southeastern Tibetan Plateau. And also modeling studies also suggest that in the by the end of this century, the glaciers in the high mountain Asia will continue to lose, and roughly 40 to 90% depending on the future climate change scenario. So in addition to glaciers, there are also a lot of permafrost landscapes here. So here from the left figure, we can see that it has community work and demonstrates that the globally permafrost is warming. So it shows the mean annual permafrost temperature change trends since the 1980s, including the Tibetan Plateau. The permafrost ground temperature has been warming, and with the permafrost ground temperature warming, and also it will result in the melt of the ground ice. When the ice of the ground ice melt, it can destabilize the landscapes, cause landslides, and also salt slumps, and to trigger additional sediment supply into the river systems. So mountain erodible landscape are also expanding. Here we introduce this concept. We define the mountain erodible landscape as the most relevant landscape, including the active glacier, permafrost slopes, and also active fluvial channels that contribute to runoff and sediment processes in cold mountainous environments. So basically, we define that the area, we use this proxy, active contributing drained area, short for ACDA, to represent the area of the mountain erodible landscape. Basically, the area below this as 0 degree isothermal line is classified as the erodible landscape, or ACDA. So in response to global warming over the past decades, we can see the area of the mountain erodible landscape, they have expanded rapidly over the past decades. Yeah. So this is the climate change and the cryosphere degradation context. And in next, I will introduce how this climate change and the cryosphere degradation, they can drive the increases in sediment supply and sediment flux. So before talking about the flux, we need to know in cold environments where are the sediment come from. So as I mentioned, there are massive glaciers here. The glacier erosion, they are super powerful erosive agents. They through plunking and abrasion, they mobilize huge amounts of sediment, and the meltwater, they can transport such mobilized sediment to the downstream. And for the permafrost landscape, such thermal urine gully or the permafrost salt slumps, they also contribute a lot of sediment, especially when such permafrost soil-related urine, they are connected with the river systems. And of course, for the riverbank urine, floodplain urine, they are also important sediment sources, especially for the ice-rich permafrost in the region. Sometimes they are also called the fluvial thermal urine or thermal bank urine, because the riverbank urine is also influenced by the changes in water temperature. So here in this left figure, if we look at this bottom figure, it shows the seasonal dynamics of the discharge and the suspended sediment. So here the blue is the discharge and the red is the suspended sediment concentration. So here I identified 5 sediment pulse events that I want to show that how in the cold environments, how temperature and precipitation, they can control the seasonal dynamics of sediment. For example, the number 1 event is a snowmelt driven event, because with temperature increase, the green line here, temperature increase drive the snow cover reduction and result in this snowmelt event. And number 2 and number 5, they are typically rainstorm driven sediment events. And for these 2, number 3 and number 4, we can see this is interesting, because during these 2 events, we can see the precipitation is close to 0, pretty low, close to 0. So, but there are 2 hot temperature windows. You can see there are 2 hot windows here. Basically, it means that the the temperature increase, they drive such glacier and permafrost processes and result in this two sediment peak events. And we also did a case study here. We first did a case study here to look at, trying to look at the multi-decadal changes of water and sediment flux in the region. Here, focus on the headwater of the Yangtze River to Toho region. And the bottom figure here, it shows the change trends of precipitation, the blue bar, the temperature, the orange dots, and also the discharge and the suspended sediment flux over the past decade. So basically, we can see all are increasing substantially, right? And for the sediment flux, from the 1985 to the 2016, it has more than doubled. From for the sediment flux increase from roughly 0.6 million ton per year to around 1.5 million ton per year. Yeah. So we know that in cold environment, temperature and precipitation, they can control the thermal or fluvial urinal processes and then drive the sediment dynamics. So temperature and precipitation are the two fundamental factors controlling discharge and sediment dynamics. Here, our question is to trying to disentangle the role of temperature and precipitation. For example, here we use a three-step attribution approach. For example, the first one is the relationship between discharge and precipitation. So we can say after the roughly 1995, if you look at the relationship between discharge and precipitation, we can see after the 1995, the slopes, there's a steeper slopes between the relation of the two parameters. It means that the discharge increase much faster than the precipitation. Similarly, for sediment flux, when we look at the relationship between cumulative sediment flux and the cumulative precipitation, we can say that after the middle 1990s, there's also the sediment flux increase much faster than the precipitation. So this demonstrates that the increased sediment flux cannot be solely attributed to the increased precipitation. The warming temperature or the warming driven melt processes must play a very important role. So in this GIL paper, we try to disentangle the role of temperature and precipitation, and our attribution results shows that the temperature increase is the major cause of the increased sediment flux in this case basin, and temperature increase contribute roughly 65%, and the precipitation increase contribute roughly 35%. And we know that in cold environments, temperature is very important in driving the thermal urinal processes and sediment dynamics. Here we also developed a model. Our model is called Sediment Availability and Transport Capacity Model. It's short for SAT model. And this work is led by Ping, and she's a PhD student in our group. And we try to simulate the sediment concentration in the cold environments. And here's the framework of our model. So basically, we try to include the thermally driven urinal processes here. So we add the temperature parameter in our model to simulate the dynamic sediment availability driven by thermal urinal processes. And our model is pretty nice, at least for this case basin. So for example, here it can very nicely reproduce the hysteresis effect between the sediment concentration and discharge. For example, here the black dots here is the observed discharge and suspended sediment concentration, and the gray line here is the simulated sediment concentration by the traditional rating curve method. So basically, you give a discharge, you have the sediment concentration. But in our model, when we add the temperature factor, we can simulate such clockwise hysteresis between the discharge and sediment concentration. So yeah, this model is suitable for the cold environments. And in the next, we collect more data from this 28 cost-pristine headwater river systems in the entire high mountain Asia. We hope to look at a big picture. And we found that in all these catchments that both mean annual runoff and mean annual sediment flux have increased substantially over the past decades. especially in the western part where they are more influenced by the westerly. You can see here in the upper Indus River Basin and upper Tarim River Basin. Here you can there are more glaciers here, so the increases in runoff and sediment flux are much faster as compared to this eastern part river basins like the Yellow, Mekong, Salmon. Yeah. Here in this figure, it can show clearly see the detailed signal. It shows the time series of the sediment flux in this bottom figure. We can see since the 1960s, the sediment flux increased slowly, and after the mid-1990s, the increase accelerated. Similarly for river runoff, also increased slowly since the 1960s, and the increase accelerated after the mid-1990s. So this is in response to the warmer and wetter climate after the mid-1990s. So you can see temperature and precipitation both their increase accelerated since then. And also the glacial melt increased since the, for example, here we also collect the glacial mass balance data to show the increased glacial mass loss and increase in permafrost degradation. So with increasing glacial melt, increasing glacial yield, and also the periglacial processes, they can trigger more additional sediment sources, and the increasing meltwater, they can transport the mobilized sediment to the downstream. And in this permafrost landscapes, there is such large scale permafrost source lumps, especially the channel connected source lumps, they can contribute a lot of sediment directly to the river systems. So in this work, we also try to analyze the sensitivity of sediment flux to climate change. We use a method called the climate sediment elasticity model. Basically, we did the sensitivity analysis for all these 28 headwater rivers. And basically, we found that for every 1 degree in air temperature, it can result in a 30% increase in sediment flux. And and interestingly, for the river basins where there are more glaciers, we found that their sediment flux, their sensitivity, the sensitivity of the sediment flux to temperature, they are higher. And basically, when for river basins, when there are more glaciers, they are more sensitive to the temperature increase. And the sensitivity, the sediment flux sensitivity to temperature change is also higher than the Arctic regions. And so based on this sensitivity result, and together with the future climate change scenario, we do the prediction about the future potential increases in the sediment flux in the region to 2050. So here is the result from different scenarios, and here is the present day sediment flux. Roughly, we estimate the present day sediment flux from the entire high mountain Asia. It is 1.94 gigaton per year, and if it is under a conservative climate change scenario, basically means that temperature increase 1.5 degree, precipitation increase 10%, and it will reach 3.2 gigaton per year by 2050. And if it is an extreme scenario, the sediment flux could more than double by the middle of this century. And also we compare our results with the sediment flux in the Greenland and the Pan-Arctic rivers. So we know that Irina Oberin, she has a very nice paper in about the Greenland sediment flux, and also updated the global land ocean sediment flux budget. And we found that for the present day sediment flux in the high mountain Asia rivers, they annually transport more sediment flux than the Greenland, and also than the bigger than the Pan-Arctic rivers. Here we compare all the 8 Pan-Arctic rivers. Okay, in the last section, I hope to discuss the impacts of the changing sediment supply and sediment flux on the hydropower systems, carbon, water quality, and the flux. And sometimes this is really the concern of our policymakers or our media, and also they really care such stuff. What is the meaning of your study? How the changing sediment flux can affect our environment and also the energy systems. And firstly, we did a analysis about to trying to look at the climate change impacts and the changing landscape instability on the or the changing sediment supply on the hydropower system. So we know For the Himalaya here, the Himalaya, we know that the Himalaya possibly has the world's largest undeveloped hydropower potential because of the heavy monsoon. Monsoon brings heavy rainfall, high discharge, and high relief here. It means a lot of energy, hydropower energy, and most of them are undeveloped. And this is hydropower are super important for these countries. For example, for the China, India, Pakistan, Nepal, Afghanistan. They're super important for these countries, especially they are considering trying to achieve the carbon neutrality by the middle of this century. And for example, for Nepal and Bhutan, the hydropower contribute roughly over 90% of the total energy source. So the question is, are these hydropower sustainable in the context of climate change? So with increasing sediment supply, they can cause the reservoir sedimentation issue. For example, we use the Upper Yangtze River as a case. We estimate that under the extreme climate change scenario in the next 3 decades, it can cause very severe reservoir sedimentation issue in the Upper Yangtze River, and similarly for other river systems. And in addition to the reservoir sedimentation, with glacial retreat and permafrost degradation, they can also cause the extreme hazards. For example, the avalanche, permafrost landslides, debris flows, and in some cases they can cause the outburst floods. For example, here, all these red diamonds in this map, they represent the glacial lake outburst floods historically occurred. So we can see all these blue dots. It means the future planned dams. They are very close to this growth size. So they are in the context of climate change, they are likely to face more risks, right? And in the past few years, there are already quite some hydropower projects that have been destroyed by such extreme events. For example, in last year, in India, the 2021 Chamoli event, February of 2021, rock avalanche and falls into the glacial valley and triggered debris flow and destroyed these 2 hydropower projects, and also caused the deaths of over 200 people. And most of them are the workers in the hydropower project. And also similarly in this Nepal, both Koshi hydropower project, they are destroyed by outburst floods, glacial lake outburst floods from the upstream. Okay, so in the future, we really need to, for the hydropower systems, we really need to be, for the design of the hydropower systems, we really need to be forward-looking to consider the possibly climate change-driven increases in sediment flux and also the changing extreme hazards. And sediment is also highly relevant to carbon. So we know that the permafrost, it is the Earth's largest terrestrial carbon sink. So with the permafrost warming, the melt of the ground ice, and the destabilizing permafrost landscapes, the increasing soil slumps, they can transport a lot of carbon into the river systems together with the sediment. And in our study, we estimate that the fluvial particle carbon in the region can reach 50 to 150 million tons per year by the middle of this century under the extreme scenario. And also sediment can affect the river quality, right? So for these headwater rivers, normally we assume that the water should be clean because there are less human activities there. But in the context of climate change, with the increasing river sediment, suspended sediment, it also means the turbidity of the river will increase. So sediment also carry the pollutants, especially for the fine grain size sediment. They are easily abounded with the pollutants like mercury, heavy metals, and potentially degrade the water quality in these high mountain river systems. And also, sediment has many implications for the floods. Now here, Jim Best, Peter Ashmore, and Stephen Darby, they have a very nice commentary paper here recently published in Nature Sustainability. Basically, they argue that when we are talking about the floods, we should not only focus on the water volume issue. So not only look at how much water in the rivers, but also look at the potential impacts of the sediment, because sediment also often determines the river transport capacity and affect the floods. For example, here, if there the increasing sediment supply from the mountain river systems when these rivers exit the mountain outlets. Here, a lot of the river slows down due to the expansion of the river beds and the reduce of the slopes. So a lot of sediment will be deposited on such alluvial fans, and with continuous river sedimentation here during extreme monsoon rainfall events, they can potentially trigger the river change of the river course, abrupt change of the river course, which is also called the river avulsion. And actually, in high mountain Asia, there are, especially in the Himalaya, there are quite a number of river avulsion examples. For example, this 2008 Kosi River avulsion. It has displaced millions of people, and similarly in the 2010 Indus River, there's also river avulsion has killed over 6,000 people. Yeah. So here is a summary of the story in high mountain Asia. So the climate here is becoming warmer and wetter, and glacial retreat is increasing, and the permafrost degradation also increasing, and the erodible landscape have been expanding. And as a result, the fluvial sediment supply have been increasing substantially with acceleration after the middle 1990s. And the changing climate change driven erosion and sediment field event is the story. Similar story is not only occurring in high mountain Asia. Here we recently did a review paper. We collect data we compared our inventory about from a global perspective and found that the climate change driven erosion and climate change driven increased erosion and sediment yield not only occur in high mountain Asia, but also in other cold environments, for example, in the Greenland, in European Alps, in the Andes, and also Alaska and Arctic coast, and also Canadian Arctic coast. So this is something we really need to think about to evaluate how this modern climate change can drive the landscape processes change so fast and affect the erosion and sediment yield in a multi-decadal time scale. And finally, I would like to summarize my talk here. So climate change and cryosphere degradation are destabilizing the icy mountain landscapes and increasing the cascading hazards and the sediment supply. Erosion and sediment flux have increased substantially with acceleration after the mid-1990s. And in a warmer and wetter future, sediment flux in high mountain Asia will continue to increase and likely more than double by the middle of the century. And the changing landscapes and the increasing sediment flux have important implications for the region's infrastructure, energy, and environment security. And we really need the forward-looking design and sustainable sediment management solutions that can help to transition towards a climate change resilient infrastructure system. Okay, here are the publications related to this talk, and some of them are not open access paper due to the limited funding. And but if you are interested in, please feel free to reach me, and I'm more than happy to send you the copy. And also, if you have any questions, I would like to more than happy to discuss with you. Yeah. Okay. Finally, I will stop here, and also importantly, take this opportunity to thank my co-authors and collaborators worldwide. And as a very young early career researcher, I really learned a lot from them. And thank you. I also take this opportunity to thank their contribution to the works. Yeah. Okay. Thank you.
Thank you, Dongfeng. This is a very, very nice and short talk. It only take about 30 half hour per talk. Then give us a lot of time for question, answer, and discussion. So colleagues, now I enable the unmute function. And if you have any question, go ahead, unmute yourself and directly discuss with Dr. Li. Yeah, Tom, go ahead.
Yeah, thank you for a very good talk, Dongfeng. I'm wondering
thank you. Yeah.
what you think happens to these sort of slumps that happen in these areas in the Arctic where you get this slumping and large mud deposition by the coast. I mean, we know a lot more about retreating glaciers and how that affects delta formation and other things in the paraglacial region, but I'm just wondering, these areas where you just have a coastline and suddenly dumps a lot of mud, has anyone looked at what happens to that area? Does it get covered with vegetation? Does it get taken away?
Okay, thank you, Tom, for your question. And you asked a question that is a little bit beyond my knowledge because
Okay.
I mainly focus on the high mountain river systems. But indeed, we in our review work, we also consider the permafrost Arctic coast. Yeah, and in the permafrost Arctic coast, the story is more complex. It is number one is because it is super ice rich permafrost, and with the melt of the ground ice, they can really cause the collapse of the permafrost. So they can have huge amounts of permafrost just falls into the ocean. And also there's another factor of the sea ice. So with the global warming, the sea ice are also shrinking. Basically, so there are basically the open water period also extended. It means that the waves can potentially cause more erosion, coastal erosion. This is another factor. And also for vegetation, I think, for the permafrost landscapes, vegetation, basically, for the vegetation, it is we are seeing the signal of greening, vegetation greening in South Pole, in high mountain Asia, and also in Arctic. So basically, there's a very nice paper. They see the Earth is greening, right, driven by the climate warming. And for the vegetation impacts on the erosion or sediment transport, I really have some concerns here. I also have some concerns here because vegetation greening, they can, in Arctic, there are a lot of papers, they argue that vegetation greening can also accelerate the permafrost thaw due to reducing the snow cover. So these are very complex issues. Yeah.
Yeah.
Thank you for your question.
Yeah, thank you for that answer. I mean, that's I understand that's not your specific area of sediment dynamics, but the other, just a really quick one thing, if I could ask one more, Paul.
Sure.
The other one is, because you're into lots of modeling and budgets, and I see you've worked with Overeem and Svitsky and some of the premier people in the world on this, and I'm wondering, do you have problems when you start sort of thinking about climate, the use of terms, like when we're dealing with climate change versus land use change or global change? So when you start talking about the dams, that's not really climate change, that's more global change.
Human.
And you sort of start linking them. I think because you're working in the high Arctic systems, it's easier to link it to climate change than if you're in Europe or the US, where you have all of these complex climate and land use overlap. But I guess this is just sort of a very general sort of philosophical question. As a modeler, do you have that problem in some of these regions you're working with in terms of the language that you use?
Okay, thank you. This is a very broad question. Talking about the global change or the Anthropocene context, we are facing not only climate change, but also there are broadly global environment change, including the global damming. Dam is booming worldwide, rivers. And in our study, because we are trying to look at the climate change signal, so in our study size, we try to focus on the pristine river systems. Basically, it means that there are no dams. We can't include the dams in the river system. If there are dams, the same flux transport will be, you will see the very sharp drop of the same flux. So we focus on the pristine river systems, and for dams, they really in the Arctic there are not too many dams, but in the high mountain Asia they are planning a lot of dams in the marginal area because these countries they want to develop this hydropower and also for irrigation. In the Pakistan, for example, Tabila Dam, a lot of the function is for irrigation. It has the world's largest irrigation system, right? So this is another big question. If we think about this question from a source to sink perspective, a whole basin perspective, we will see, at least in the case of high mountain Asia, we see the increasing sediment supply from the high mountain glacier retreating, permafrost degradation. But in the marginal area, we see a lot of dams, so they will trap such a sediment. So in the middle lower part of the river, there are hungry water drives the urine at the delta is shrinking, such kind of issue. Yeah. Thank you for your question. Yeah.
Thank you.
So anybody else? Dongfeng, follow that Tom's question. You are right in the from the source to sink scheme. When you have a strong signal happened from the source, there's always many buffer or modifier in the middle. When they reach the sink, could be completely changed. Maybe some still keep, but you are lucky. You're working on mainly on the upper reach. That area mainly driven by climate change, not too much human activity, like a glacial and increase the sediment flux. But you have such a great team, as Tom pointed out. But one more question I ask for Tom. Is any member, any of your team, look at of the biochemical signature? For example, with all, not only the sediment flux change, how about the carbon, how about other chemical elements, any other those signature at the same time to observe? That's important and very lack the field data.
Is the question for me or for Tom?
For you. I mean,
okay,
I ask for Tom. Tom very interested in this, I guess.
Okay, thank you. Yeah. I'm not a carbon guy. Yeah, I'm sediment guy. Yeah. That's a big issue. Yeah, with increasing erosion. So if we think about the weathering and also the solute dynamics here, and there's I think in last year there's a Nature communication paper. They found that with glacier increasing glacier melt, and they found the increasing chemical weathering in the proglacial area, and the increase of the solutes. I'm not exactly sure what solutes they have, but yeah, they have such a preliminary finding from a global perspective, and I think this is really a big issue. Yeah, big question. Yeah, a big area to explore if we have the data. Yeah.
Yeah. The Cambridge that they have the river watching group. They try to work on the Himalaya, even including Greenland, try to see. And I mean, your work definitely for your future, you should consider some colleague doing that kind of. You get a water sample, don't waste them only for sediment flux, but we definitely need to look at the biochemical signature.
Yeah, I mean, Paul, I think that's of course I'm very biased on this, but I think that is something that needs to be better linked with a lot of the source to sink, more sediment focused models. And I think now that we're getting more information, some of these papers, Dongfeng cited and Savitsky's 2022 paper and Dongfeng's papers and some of these other ones are really giving us these really nice budgets now. And so now it's really time for the biogeochemical people to step up and start talking about, as you start pooling mud in different places and the residence time as it sits in different locations, we're changing the whole pathway of how mud moves around the planet, where it sits, and how much burning and how much burying is going on with the carbon. And we're actually putting a review paper I've been working on for over a year with some people, but it's just very difficult to write. It's very, very difficult to write because we just don't have a lot of numbers. And when you really get into the details of how the particle size and residence time and all of these other factors, when you try to summarize that in a review paper that actually provides something to the reader, there's more questions than answers. And it's so very, very difficult. So we're trying to see what we can do so we don't have an empty skeleton and just put that out. And we're trying to increase that. But I think, Paul, you're right on target with saying that that's needed. That's one of the messages in the paper that we have, is that we need to link all this information now with this movement of mud. So I agree. Yeah,
I think, at least this platform, I think give opportunity for all this kind of storm, brainstorm. And Dongfeng, one more question. I mean, this is maybe a little bit easier. So when you see the flux change, how about the nature of the sediment? For example, the grain size. You know, is of course is not easy to get a total number flux, but we need more. We cannot stop here, said only the total amount change. How about the nature of the sediment? Like more, how about the sorting of the sediment? How about the grain size? How about the clay, you know, components? I mean, this is a further question we need to answer.
Thank you, Bob, for this really excellent question. Yeah, this is really something we need to explore. And for our study, we only focus on the suspended sediment because we in the high mountain rivers we really don't have any observation of the bed load. Yeah, but we sometimes we were questioned by the reviewer that you only focus on suspended sediment, but how about the gravels? Yeah, we don't have the data. And for the bed load, they really vary in the high mountain river system. They vary with a lot of factors. I think Sagi Cohen, they really recently have a paper published in WR from a global perspective, trying to model the Sagi Cohen and also Jasalaski. They trying to model from a global perspective, model the bed load and the flux. I think this is really challenging, but because we don't have the observation of the grain size in a sufficient resolution. Yeah, but this is a very good question we hope to explore. In the middle lower part of the river system, they have the grain size analysis, very careful analysis. I think in Thomas is from the BFG, a German guy. In his talk, he talked about the detailed budget of the river run, right? Different size of the sediment, different, clay budget, coarse sediment budget, but in here we don't have the data. Thank you.
Okay, good. Next proposal. Okay, so anybody else? Yeah, please, if you have any question, just go ahead to unmute yourself.
Yeah, can I ask a question?
Dongfeng Li, go ahead.
Yeah, sure. Great talk first.
Hi.
So you were talking about increasing sediment flux and changing the landscape during the maybe the temperature and the precipitation increase. I'm wondering, have you looked into or thinking about the feedback of landscape on precipitation or hydrological cycle, like how the landscape will change the partition of precipitation into runoff, and it will be a positive feedback or negative feedback? How do you think about that?
So sorry, can you I didn't get your question very clearly. How the
landscape will feed back to the hydrological cycle, like the runoff and the partition from precipitation to runoff.
Okay. Thank you for your question. This is I think this is something beyond my knowledge. And normally we talking about the feedback in the landscape evolution. There are a lot of feedbacks. For example, with the retreating of the glaciers, they can increase the same supply from the valley glacier. But on the other hand, they form the alluvial fan in the downstream. So such alluvial fan, they can form a negative feedback to they can redistribute the rivers and slow down the stream power and a lot to form such kind of negative feedbacks. And Stuart Lin, he has a very nice paper in geomorphology to explore this issue, to discuss how the glacial retreat affect the sediment connectivity. But how landscapes can feedback to landscape change feedback to climate or hydrology, I really don't know. But thank you for your question.
Got you. Thank you.
Okay, anybody else? Okay, if no further question or comments, and thank you, Dongfeng, again. And this is a fantastic, and it's very inspiration. And so I think we will read carefully your work, and then we see, maybe we can develop some collaboration.
Sure, you're more than welcome. We should invite you.
So Tom, we still tomorrow 9 o'clock? Oh, yeah, okay. So see you tomorrow. Okay. Okay, then, okay, great. Thank you, everybody. Oh, by the way, if anybody here, want to give a talk next Wednesday, and we still that slot open. If you have a postdoc, anybody, or if you want to give a new update talk, welcome, let us know. Next Wednesday, so far we don't have any speaker, but we can have a break, but it will be nice to have somebody give a talk. Okay, if you have somebody you want to recommend it, go ahead. Okay, cool.